Circular motion, exercise question 24, from H.C. Verma. Here is the cross-section of a hemispherical ball of radius r, rotating about its vertical axis. A small block of mass m sits inside the ball, at a position where the radius makes an angle theta with the vertical. The block moves in a horizontal circle of radius r sin theta. The forces on the block are, the normal force N, pointing toward the center of the ball, the weight mg acting downward, and friction F along the ball surface. Friction can act either upward or downward along the surface, depending on whether the block tends to slip down or up. The question asks, a hemispherical ball of radius r is rotated about its axis of symmetry, which is kept vertical. A small block is kept in the ball at a position where the radius makes an angle theta with the vertical. The block rotates with the ball without any slipping. The friction coefficient between the block and the ball surface is mu. Find the range of the angular speed omega for which the block will not slip. The key concepts. The block moves in a horizontal circle of radius r sin theta. The centripetal force needed is m omega squared r sin theta. Now, there are two extreme cases that determine the range of omega. Case 1, when omega is too small, the block tends to slide down the ball. Friction acts upward along the surface to prevent this. This gives us the minimum angular speed, omega min. Case 2, when omega is too large, the block tends to slide up the ball. Friction acts downward along the surface. This gives us the maximum angular speed, omega max. Case 1, the block tends to slip down the ball surface. Friction acts upward along the surface toward the rim. Vertical equilibrium gives n cosine theta plus f sin theta equals mg. Horizontal centripetal equation gives n sin theta minus f cosine theta equals m omega squared r sin theta. At the verge of slipping, f equals mu n. Substituting f equals mu n into the vertical equation, we get n times cosine theta plus mu sin theta equals mg. So n equals mg divided by cosine theta plus mu sin theta. Now substituting into the horizontal equation, n times sin theta minus mu cosine theta equals m omega squared r sin theta. Solving for omega squared, we get omega min squared equals g times sin theta minus mu cosine theta divided by r sin theta times cosine theta plus mu sin theta. Dividing numerator and denominator by cosine theta, we simplify to omega min equals the square root of g times tangent theta minus mu divided by r times 1 plus mu tangent theta. Important note, omega min exists only if tangent theta is greater than mu. Otherwise, the block won't slide down even at zero angular speed, so omega min is simply 0. Case 2, the block tends to slip up the ball surface. Now friction acts downward along the surface, toward the bottom. Vertical equilibrium gives n cosine theta minus f sin theta equals mg. Horizontal centripetal equation, n sin theta plus f cosine theta equals m omega squared r sin theta. Again, at the verge of slipping, f equals mu n. Substituting f equals mu n into the vertical equation, n times cosine theta minus mu sin theta equals mg. So n equals mg divided by cosine theta minus mu sin theta. Substituting into the horizontal equation, n times sin theta plus mu cosine theta equals m omega squared r sin theta. Solving, omega max squared equals g times sin theta plus mu cosine theta divided by r sin theta times cosine theta minus mu sin theta. Dividing numerator and denominator by cosine theta, we simplify to omega max equals the square root of g times tangent theta plus mu divided by r times 1 minus mu tangent theta. The answer. The range of angular speed for which the block does not slip is omega min less than or equal to omega less than or equal to omega max, where omega min equals the square root of g times tangent theta minus mu over r times 1 plus mu tangent theta, and omega max equals the square root of g times tangent theta plus mu over r times 1 minus mu tangent theta. If tangent theta is less than mu, then omega min is simply 0. Exam tips. First, whenever a block sits on a rotating curved surface, always consider two friction cases, the block tending to slip up and tending to slip down. These two cases give you the range of angular speed. Second, remember to resolve forces along the normal and along the surface of the ball. The normal force N is perpendicular to the ball surface, not vertical. This is a common mistake. Third, always check limiting cases. If mu equals 0, there is only one allowed angular speed. If theta equals 0, the block is at the bottom and there is no circular motion. Like and subscribe for more circular motion solutions at MAGPIEHUB.